everyone. So, welcome. It's my pleasure to introduce Professor Lucas, who's a friend and a collaborator from the group since some time. So, I will introduce you very briefly. Professor Lucas did his PhD in UFSCar in quantum open systems and dynamical Casimir effect. After that, he spent 4 years in Irreversibility Ce doing his postdoc, working in quantum information, general relativity, foundations of quantum physics and thermodynamics. And since 2012, he's a professor at UFG, Universidade Federal de Goiás, where he's the leader of the QPQ. PQ is, for those that don't know, it's
I will explain.
Yeah, okay, great.
Everybody asks.
Yes. And I mean, since then, he has established a lot of collaborations nationally and internationally. Has been visiting professor in Bilbao, Singapore, and other places. And he's going to spend 2 months here at the institute with the grant funded by Simon's Foundation. So he has spent already 3 weeks, I guess, or 1 month. We'll stay a bit longer. So I know that many of you have already knocked at his door a few times. So I guess he doesn't mind. So
Yeah.
keep continue doing that. So today is the first of a series of lectures that will take place the whole week at the same time, apart from Friday when it will be at 9 instead of 10. And the reason is that at 11, Lucas will give a colloquium. So, yeah. And please ask questions during the lectures. The idea is to be as informal as possible. It's going to be recorded, and it will be in the YouTube channel of the Institute at some point. Yeah, so if I'm not forgetting anything, please, Lucas, and thank you very much.
Well, thank you very much for the nice introduction. Thank you, all of you, for being here. Well, as I told you, I'm visiting here, and first of all, I need to ask sorry for this thing. As obviously we are not in Santander, but I use the same, basically the same Beamer presentation, so I just need to change, and I forgot to change the name of the city here. So I intend to give a series of 5 lectures, and Rafael told me that to be very basic here, so I will start with the basic things in fluctuation theorems, but the very basic ones in statistical physics, regular statistical physics. So introduce these things, what we mean by fluctuation relations and why they are important. And then it starts the core of the course that is general relativity. I think that most of you don't have contact with this. So I intend to give a brief introduction to the field. What is general relativity? Why GR is the way it is, and how we do calculations, basic calculations on this thing, and why we have a deep problem in thermodynamics in relativistic context. Why we still today we don't have a thermodynamic theory in full relativistic context. It's really a huge problem, and then I wound up in the describing a theory that we proposed that is able to describe the thermodynamics of a quantum system living in a curved spacetime. But until that, I need to convince you that gravity and spacetime is the same thing, and this thing must be curved. And also, the starting point is the fluctuation relation. I intended to, take 1 hour, 1 hour and something, but please interrupt me at any point. I actually prefer just raise your hand and ask questions. Okay. So first of all, acknowledgements. So that's my colleague in Santa Maria, Jonas Maziero, that was here in the beginning of the year, visiting the institute. That's Marcos Basso, which is the student, PhD student at Federal University of ABC, UFABC, in Santo André. And And here's, of course, funding. I would like to thank you, Rafael, for inviting me and the Institute for hosting me. And I mean, all of people that contribute with money in these things, otherwise it's not possible. Okay, and then the second thing, as I told you, I start with basic thermodynamics, classical and quantum versions of the fluctuation theorem in linear response and also out of equilibrium, and which is the fully general. There is a mouse here, no? No. Okay. And then basic relativity. Basic relativity. I mean, what's general relativity? And a very, very, very simple introduction of this. I mean, every one of these topics should take an entire course, but we don't have time for this, so I just a brief introduction to the theory, with a hopefully it will be understandable. And then relativistic thermodynamics, which is the main problem that we are creating here. I mean, how we deal with thermodynamics of quantum systems that live in a curved space-time. So, by the way, these slides and I also prepared lecture notes for these things where I open all the calculations that I will show here, so you don't need to care about the details of the calculations, because I will upload these in my website today. So both the slides and the notes with the calculations, the entire calculation, so you can access this. The website is qpk.com. So in the teaching part, you can access this thing from this afternoon on. So that's it. So that's the plan of the thing. The first thing that everybody asks me all around the world is, I mean, what is Pequi? And as Rafael told him, the name of the group is Quantum Pequi. And here you have an atom, and here you have the Pequi at the core. So what's Pequi? Pequi is a fruit that, I mean, came from these tree over here with the flowers, very, very beautiful flowers, and it occurs in state of Goiás and north of Minas Gerais, and that's it. So that's that. You can only, and Goiânia, that a city where I come from, it smells like Pequi. I mean, we have Pequi everywhere. They sell Pequi everywhere in the city, so it smells like Pequi. It's very tasteful, actually. Pequi is this thing. That's the flower. That's the fruit. We ate only the shell of this thing because inside the shell is full of spikes. So I don't advise you to eat these things unless you know exactly what you are doing. Otherwise, you go to the hospital. A bunch of tourists end up in the hospital because of these things. So we use this everywhere. I mean, rice, chicken. We made a beverage, ice cream, and a bunch of other things. So it's impossible for you to go to a restaurant and not eat Pequi. Everyone has Pequi. Pizza with Pequi, Pequi everywhere. So that's why I call it my group the Quantum Pequi. That's okay. Now you know what Pequi is. Let us see what thermodynamics is. Okay, thermodynamics is a very particular theory in physics. I mean, while we have a quantum mechanics, general relativity, or any other fundamental theory of physics, thermodynamics is not a fundamental theory. Thermodynamics doesn't care about the dynamics of microscopic degrees of freedom. Thermodynamics cares about a description of macroscopic systems through a very few amount of variables, not thermodynamic variables. How these things emerge. Every theory, we need to specify what kind of questions the theory is allowed to answer. Thermodynamics is allowed to answer macroscopic questions. What are those? Well, space and time measurements. They are not able to follow the microscopic dynamics of the system. I mean, the fluctuations in the position the volume of this table, for instance, we cannot measure them with macroscopic instruments. Also the time. I mean, the time of these fluctuations here, the characteristic time of these guys, is much smaller than the time that we take to make measurements. So in the end, what we measure is our space and time average. From this procedure, the thermodynamic variables emerge. So this is the coarse graining that we're talking about in thermodynamics. So one of the problems in describing thermodynamics in the quantum regime is precisely to describe these sort of things. I mean, how to properly introduce coarse graining in this thing. We'll talk about this on the colloquiums Friday. But here we just take the macroscopic view, and we have a set of time independent variables that emerge from this thing, this procedure. Those are the thermodynamic variables that we have. It's amazing that we have just a few of them that are able to describe the entire system. That's amazing. That's what why thermodynamics is called universal theory, because it simply doesn't care about the dynamics of these guys. I mean, if these guys are following classical mechanics or quantum dynamics, it doesn't matter. I mean, the result is going to be the same because of the coarse grain. It washes away everything. That's why thermodynamics is so powerful the way it is. So these are the basic laws of thermodynamics. The first thing is equilibrium state. I mean, we have to state what kind of things we are dealing with, and thermodynamics deals with equilibrium states. And equilibrium states is very easy to define. And if a macroscopic body is in equilibrium, thermodynamic equilibrium, then all net fluxes inside the body vanish. This implies that temperature is the same all over the body, pressure is the same all over the body, and volume is constant, and things like this. The second postulate is entropy. So we just postulated that exists a function which we call entropy with these properties here. We postulate the mathematical properties of the function, and we call this thing entropy. And this is a function of the few extensive parameters that you have in equilibrium states, in equilibrium thermodynamics. This is all equilibrium. There is no way to define this thing. Nobody knows how to define this thing out of equilibrium. Actually, we know how to define many of these things, but once you have many functions, infinitely many functions, it's the same thing that you have none. So, and so we postulate the properties of this guy, especially that's monotonically increasing function of the energy, and it's additive for independent subsystems. And then these guys define it only up to a multiplicative constant and an additive constant. So we fix the additive one by stating this thing, that entropy goes to zero when temperature goes to zero, and temperature is defined as the derivative of the internal energy with respect to this guy. So there is no way to this guy be negative, because, I mean, the postulate states that a monotonically increasing function of energy. So the temperature is defined as the derivative of the energy with respect to the entropy. So there is no way this guy is positive always. It's a consequence of the postulate. So this is basic thermodynamics we see in every textbook. Okay. And when this happens when the system, the number of degrees of freedom in the system goes to infinite. So fluctuations vanish, because fluctuations is simply you define the variance of certain quantity, like the energy, and divided by the value of this quantity, the expectation value of this quantity. This goes with 1 over square root of the number of degrees of freedom. So in the thermodynamic limit, the number of degrees of freedom goes to infinite. Fluctuations vanish. So we don't care about the fluctuations. That's what you call the thermodynamic limit. But then fluctuations goes to zero. We don't care about fluctuation theorems. We don't care about anything because I mean fluctuations vanish. But there are situations in which fluctuations do not vanish actually. I mean small systems and a small, not a single atom or things like this, but a big a big molecule or a protein that thing is big enough for us to not be able to describe it following the microscopic dynamics of the degrees of freedom. It would be a huge amount of differential equations, so we cannot solve this thing. But we can treat this thing with statistical mechanics, which is still in equilibrium, but fluctuations plays a role here. So let us study the role of fluctuations. Well, at equilibrium, a statistical mechanics says that we have a gas here, or particles, a bunch of particles, very weakly interacting particles, and at thermal equilibrium, these guys will have a distribution of velocities. These distribution of velocities follow this law here, which is Maxwell-Boltzmann distribution. So due to the isotropy of space, these guys should be a function only of the absolute value of the velocity. It cannot be a function of the velocity itself, otherwise isotropy would be broken. And then it's this guy is just a constant with a function of the mass and the temperature of the gas. So here is beta, and beta is the inverse of this guy. Boltzmann constant is equal to 1, because I mean I can simply put Boltzmann constant equal to 1 and dimensionless by simply defining temperature in terms of energy, in units of energy, then everything is okay. So I don't need Boltzmann constant here. The question that we are, all of these images were generated by ChatGPT. I mean, this thing is very good to create images. So the balancer here stands for equilibrium. So the question, yeah, yeah, equilibrium. And that's the distribution of velocities. So the question is, what happens out of equilibrium? I mean, what happens when you take the system out of equilibrium and let it thermalize again? We are interested in quantifying entropy and irreversibility in these sort of processes. That's not actually thermodynamics, but we are interested in the response of the system by taking it out of equilibrium. Because out of equilibrium, we cannot simply define thermodynamic potentials like entropy or any other free energy or any other thermodynamic potentials. Not even internal energy we can define. Because, I mean, all the thermodynamic potentials are linked through legendary transformation. So if we define one of them, we define all of them. So we cannot define entropy, we cannot define any one of them. But we can study the response of the functions when we take the system out of equilibrium. That's the idea of the out of equilibrium thermodynamics. Let us see how we do this. So, questions until now? Nope. Okay. So then, from here to Friday, we rely on these assumptions, these two basic assumptions. I mean, the initial state of the system is the thermal equilibrium one. That's the Boltzmann, that's the partition function. That's the which partition function, there's the trace of this guy, or the integral of this guy in classical physics, and over the entire phase space, and which just a normalization of the probability distribution. And H is the Hamiltonian of the system, the classical Hamiltonian function, or the Hamiltonian operator. Of course, I will assume this thing, but all of the things that that follows from here can be also derived including other ensembles like microcanonical ensembles, grand canonical ensembles, or generalizing equilibrium ensembles. It doesn't matter. The only thing that matters is that the initial state is in equilibrium. So we have a reference state because we want to study what happens when we take the system out of this state. So we need a reference system. It's equilibrium state. And this is a very important assumption. The microscopic dynamics is reversible, which means that it follows classical dynamics like Hamilton equations, which are reversible, or quantum dynamics, Schrödinger equation. So it's reversible in time. So this is microscopic dynamics reversible. This is a very important assumption, and it's okay because I mean all the fundamental theories of physics that we know are reversible in time. It doesn't matter if you change the sign of time; it's the same thing. So these two assumptions will be under everything that follows. Okay. No. Oh, that's an important question, but measurements will play a role in the definition of the quantum fluctuation theorem, and this is a matter of debate today. I mean, this implies how to define energy and how to define the other things, because I mean, when we introduce measurements, uh, as you told it, then the dynamics is not reversible anymore. But when we describe the quantum version of the theorem, what happens is that the only thing that matters is things that happens between measurements. Is the way we use to define things. So this thing is that happens between measurements should be reversible. A measurement is a macroscopic thing, but we discuss this in the end of, remember me in the end of the, when we get the quantum part of it. Okay, so we enter in fluctuation relations. When this started with Einstein itself in the famous paper of Brownian motion. So Einstein was studying the strange behavior of particles in a fluid, suspended in a fluid, and it looks erratic motion, and this paper is fundamentally important because it's the origin of statistical physics. Actually, until this paper, we as scientists, we simply didn't accept the existence of the atom. Here, with this thing, Einstein postulated, no, it must exist this thing. And then it started the entire statistical physics, actually. And if you read Feynman's lectures on physics, I think that the first or second chapter, it asks us what's the most important statement in physics. I mean, if everything would be destroyed, and you can say just one statement, what would be this? And Feynman put there exist atoms. He said that's the most important statement in physics because you can derive a bunch of other things from this. And this thing was born here, actually, in this paper. That's why this guy is absolutely fundamental. So I will not present the derivation of this guy here. It's simple, but they're not presented. They are the derivations in the notes through Fokker-Planck equation, and it's not difficult to derive this thing because it's in equilibrium. We are very close to equilibrium, and Einstein starting at equilibrium, and then the system is driven out of equilibrium, weakly out of equilibrium by a force, and the response of the system is determined by the fluctuation properties at equilibrium. So what does this mean? This means that equilibrium determines the response of the system, and the force is arbitrary, except the fact that it's weak. But then after many years, we have a general fluctuation theorems, which says the same thing, but arbitrarily far from equilibrium. So the properties of equilibrium determines the response of the function. That's the content of this equation. This is the diffusion coefficient of the mean, and that's the drift velocity. Okay, and F is the absolute value of the force. So that was the first fluctuation relation, which is called the Einstein relation, or like this. Few years before this, 1928, these two guys that have the same sort of relation, but in electric circuits. What means that since the temperature is not zero, electrons will have fluctuation. The position of the electrons fluctuates. So it's an electric charge. Electric charge that's accelerating and generate a fluctuating electric field and a fluctuating potential. So the fluctuations, the variance of the fluctuations is given by this relation. Here is the resistance, and delta E is the bandwidth. So this is also derived in the notes. But you see that's the same thing. It's exactly the same thing. And then many years after this, we're talking about 50s, yeah, 50s. We have a Green and Kubo that derived the actual fluctuation theorem in general, but for linear response theory. So what's linear response theory? Linear response is just this thing. This, the theorem itself provides this connection, with the same connection that we just saw, but in general, for every system. So we describe the system like this, is the Hamiltonian. It doesn't matter if it's a quantum or classical, it's the same thing. And this is the perturbation. And the only thing that we say is that age, the small age, is small. So the perturbation is very small. We take the system weakly out of equilibrium. So that's why it's called a linear response theory, because we are just want to study the linear response of this guy. So the system is in terms of equilibrium with this guy here, because the fluctuation, the perturbation is not turned on yet. So the system is there. And then we turn it on the perturbation and said how the system responds to this. This time-dependent field here. And we do this by looking at another observable. I mean, how this observable responds to the perturbation. That's the idea of the entire theory. So that's Liouville equation in interaction picture. Basic quantum mechanics, and then we solve this guy in first order. I mean, you just integrated this guy, pick up the result, and put again into the integral differential equation, and take just the first order in this guy in small h. The rest we simply throw away. That's why it's called a linear response. It's here the approximation. We just keep this guy here. And then it's easy to compute the expectation value of any operator. Is just like this, basic quantum mechanics. And then we define the important thing, which is the response function. So the response function is just defined like this. You see that here is the commutator of the operator and the perturbation, because we just want to know how this guy responds, and we know that the dynamics of the commutator gives us this thing. This theta function here is here because of causality. I mean, it means that this guy cannot change before the perturbation is turned on. So that's the reason that the step function, this is the half side or step function, that step function. That due to causality things, they are here. So we just, compute the perturbation that we want with this guy. And the equilibrium, the correlation function is given by this guy. We just want to see how the relations between space and time separated points responded to the system. So we need to use the correlation function between these guys. And from this, we can define simply the spectral power, which gives the same thing, but with respect to the frequencies of the system. No, it's just the Fourier transform of the guy here. That's the basic theory. What the theorem by Kubo and Green said is this: it relates the imaginary point, the imaginary part of the response function with the spectral function. We just say this thing. This is because of equilibrium. This is just the distribution of equilibrium. This was proved here in these papers, 1954 and 57 by Kubo. And this is what we call the fluctuation theorem in linear response regime. So that's the main idea of the guy. So if you have a system that's weakly perturbed from equilibrium by some force, random force, the response of this function, the response of this system is going to be exactly the same as you pick up this system and put in contact with a thermal equilibrium. So there will be dissipation, there will be these things, and the theory balance will simply break. It's recording.
So trying to do the same computation in the classical mechanics case would be the substituting the initial Gibbs state as the Liouville distribution of the Hamiltonian?
Oh, it's exactly the same. Gibbs state, but Gibbs state is exactly the same thing. I mean, but instead of the Hamiltonian, you put the energy there.
Right. And the definition of the correlator?
The commutator would be the
Poisson. Yeah. Okay. Yeah.
But it's exactly the same. The result is the same. This holds for both. It's actually as we will see in a bit, every fluctuation theorem has exactly the same form in classical and quantum dynamics. But, so that's the general theory. Let us go to Crookes theorem. This is 1998. This is the general theorem that gives you the response function, the fluctuation relation theorem for every order, not just linear one. So let us see how this is derived. I will derive the simplest form of this guy here in classical and quantum physics, and then by the end of the course, I will derive a more complex one. So, but for today, this is enough. So those are the assumptions. Let us start with the classical physics. Classical systems have phase space coordinates x. Okay? Microscopic phase space coordinates. The evolution is governed by some Hamiltonian. And this lambda here is some parameter that you can externally control. I mean, like magnetic field or anything that we can absolutely control. So we are performing work on the system and things like this. And this process, this is what we call process. I mean, the thermodynamic process. So the system is there at equilibrium, then we take the system out of equilibrium by turning it on this guy, whatever it is. And then we ask what happened with this guy. So the system is prepared in this thing, so that's the answer to your question. It's, I mean, classical distribution phase space. And dynamics, of course, is microscopically reversible and Markovian because it's Hamiltonian flux. Nothing changes here. So that's the setup that we have. We are interested in only this setup. Is going to be the same setup in quantum dynamics, just change the equations. But well, so now we need to define two processes. Why we need to define the reverse and the forward process? Because we are interested in entropy. We are interested in studying how reversible the process is, or how irreversible the process is. So how we define reversibility. Reversibility is defined in terms of how well can I distinguish between the forward and the backward process. I mean, if I can distinguish these guys, for instance, a pendulum that's oscillating, if I recorded this guy, it's always be like this. I mean, neglecting a noise or anything like this. So it always be like this. If I play the video in forward or backwards, it's going to be the same. You cannot say the difference between these guys. This is the definition of reversibility. This is a reversible process. So we needed to distinguish between forward and backward trajectories. That's That's how we define entropy out of equilibrium. So that's why you needed to define these guys. And the forward process defined it the way we are used. The system evolves forward in time with this guy from lambda 0 to lambda tau, whatever it is. The reverse, and then we study things. The reverse process is defined in this way. Here we just reverse the evolution. We start at this parameter at thermal equilibrium defined with this Hamiltonian, the final Hamiltonian, and then go backward in time. This process never happens. This process happens. This process is just a reference process. If you can tell apart these two guys, then entropy will be produced in this process. There is no way. So the equality between these guys here is what you call detailed balance. So the probability of being forward and backwards is exactly the same. You have the same trajectories, so you cannot distinguish between past and the future. Your process doesn't generate entropy. That's the main idea here. That's why we needed to define these guys. But the physical one is just this one. So then we denote the trajectory by gamma in phase space. And the probability, just these guys, is the probability of forward. And the probability of the reverse is just this guy with the reverse trajectory. Just, usual probability definition in phase space. Questions? Oh, okay. So, or you understand everything or anything? I hope that, no.
So essentially, what this Crookes theorem says to us that if you have some kind of microscopic reversibility, then the probability distribution of the entropy production in the forward process is some kind of exponentially greater than the entropy production in the reverse process, something like that.
Yeah,
if I understand well.
Crookes theorem, which is not here yet, but it says in terms of entropy. R. This guy. Sigma is the entropy. But the statistical entropy. This is a fluctuating quantity.
This P is probability.
This P is this probability here, but the probability of observing the forward process, in the forward process, an entropy production of sigma. Because and this is the probability of observing in the reverse process, the entropy production of minus sigma, which means decreasing entropy. So what this guy says is that while this guy is possible, because the probability is not zero, it can occur, we can simply observe a process in which entropy decreases. That doesn't matter. This is not a violation of the second law. But these guys are exponentially suppressed. On average, if you repeat the process many, many times, the entropy will increase. The average entropy will always increase. That's the second law of thermodynamics.
Yeah, I think it's because you are looking to the trajectories, right? The space trajectory, and you can see the time reversal trajectory or something like that.
Yeah. Well, it comes from there, but it's independent of the trajectory. The quantum case is going to be the same thing, and we don't have trajectories.
Okay. Thank you.
So how do we build this thing actually? In quantum mechanics, in classical mechanics, it's easy to define work. So that's the work performed on the system or by the system, it doesn't matter, during in the trajectory gamma. So it's just the integrated power. It's just work. We define this thing in, basic courses in physics. Just integrated power. You have the work. In quantum mechanics, it's going to be a little bit different, but we get there. So if we define this guy as the difference in energy between the initial and the final, the final stage, It's just the energy that changes. Then the heat is this guy. Just the first law of thermodynamics. Conservation of energy. Heat is whatever is not work. We call heat. In classical mechanics, it's easy because these guys define it, these guys define it, so these guys uniquely define it. So we assume this thing, detailed balance condition, which is possible to prove by just computing the ratio of probabilities. This is computed in the notes. The equation is there. This is what we call detailed balance. Remember that this guy is equilibrium distribution. From this, we can derive Crookes relation. We derive this guy, which is equal to this guy. We just here write this guy like this. That's the partition function defined with the final Hamiltonian. That's the partition function defined with the initial Hamiltonian. Because the Hamiltonian can change during the process, so the partition function also can change. So we just write this thing. This guy is the difference in free energy. Is equilibrium quantity. It's just the difference between these guys here, the ratio between these guys. This is how equilibrium things determine non-equilibrium quantities, because work is out of equilibrium. But the equilibrium thing appears here. With all of these things, we can define this guy, the probability of work. So work is a stochastic quantity. If you consider every trajectory, have fluctuations there. Fluctuations don't matter. Work becomes a stochastic quantity. I can define it the same way. And I can define the probability distribution of this guy, which is just, from the rules of statistical mechanics, we just defined the work like this, the probability distribution of work like this. That's the way how we go from one stochastic quantity to some other, one stochastic quantity to some other one. That's the way we do this in statistical mechanics. The same thing holds for this guy here. So it's the probability of getting work from the system during the reverse protocol. So we just define it. There is a missing minus sign here. So it's supposed to be minus this guy, like this guy. So we can simply here write this thing using the ratio of the probability that you just saw in the another slide, which is this guy here. This guy here, or this guy is the same. So he write the guy like this, and then we simply get Crookes relation. That's the entropy production. It's the work minus the difference in free energy. That's the way we define entropy in usual thermodynamics. But here we should remember that this guy is a stochastic function, while this one not. So that's actually the meaning of the second law of thermodynamics. If entropy is zero, we cannot distinguish between the forward and backward process. It's exactly the same thing. So there will be no irreversibility, there will be no entropy production. But in general, observing this guy is exponentially suppressed. So we have a huge probability of observing the forward process, not the backward, and not entropy being decreasing. Although you can actually observe entropy being decreased. This doesn't mean that we are violating the second law, because the second law is a statistical statement. It doesn't hold for every process. It holds on average. And that's the content of this guy. So once the equality between this guy and this guy is also called the detailed balance. So dissipation occurs when the detailed balance breaks down. And dissipation must be accompanied by generation of entropy. Remember that this sigma is a stochastic quantity. So this is what we understand today as fluctuation theorems. Detailed fluctuation theorems is this guy, because it holds on the level of probabilities. And the other famous theorem that we have is Jarzynski relation, which actually was published before, but I mean, it follows from Cook's theorem simply by integrating because of conservation of probability. Then from Crookes relation, we have this thing, which is the Brzezinski equality. I'm sorry for not putting the reference here. I will update the slides before upload it in the website. But this is published in 1997 by Brzezinski, and it's called today by Brzezinski equality, and it has been studied several times experimentally in many contexts. The first one was to solve a problem that we have in protein folding. I mean, one of the most important things that we have today in protein is I have what's the three-dimensional configuration of a protein. I mean, we simply don't know. It's extremely hard to compute this guy, but we postulated that this guy is minimized at this configuration, the best configuration that we have. So how the guys did it is the guy used an optical tweezer to just, pick up the two ends of the protein and, just stretch and release. So they measure the work that they were doing during stretching the thing. By doing this many times, they can measure this thing. So they can compute this average. From this average, they can compute the free energy, which is a huge problem. We cannot compute this from, microscopic dynamics. This is impossible. It's a huge number of molecules, of atoms. So this was the first thing that they employed this relation. And it's clear here that no matter how far you are from equilibrium, because W can be whatever you want. The process can be whatever you want. No matter how far you are, the average of this quantity is determined by equilibrium things. That's a very powerful statement in this thing. Equilibrium matters. It matters a bunch. So from this thing, since this guy is convex, we can simply derive this quantity with the first moment of this, the probability distribution. And this says just that the average entropy always increases. That's the second law of thermodynamics. On average, always. Average here over the ensemble of realizations of the process, of course. So that's the content of the Brzezinski equality, which called the fluctuation theorem, and Crookes we call detailed fluctuation theorem because it's the statement on the level of probabilities. Oh. Okay, questions? Before we enter in the quantum case.
Yeah. You have some intuition, especially in Crookes' theorem, that you assume that the dynamics is reversible. The dynamics is time reversible. And when exactly the irreversibility emerges in the Crookes theorem?
I don't know if I really understood your question about intuition about the reversibility of the dynamics, the microscopic dynamics, because we are assuming that the microscopic degrees of freedom follows or classical mechanics in this case, or quantum mechanics, which are reversible.
Yeah.
So there's assumption. We are just assuming a classical physics hold or quantum physics hold.
Yeah.
Just this. That's the assumption that lies in the micro-reversibility.
Yes, I think that I could make a better statement. Where the irreversibility shows up in the probabilities.
Okay. This is a good question, actually. That's because we cannot track fluctuations. We have fluctuations that you cannot track them down, and when these guys enter in the calculation, what happens is that you simply lose information. That's the way I understand the things. And then and then irreversibility emerges from this guy. So irreversibility, it emerges from lack of information that you have due to fluctuations that you cannot control.
Yeah, so in the backwards process, you lose more information.
Well, no.
No.
The backward process is just a reference one. It never happens because you cannot simply reverse time. I mean, the backwards is just a reference one.
Okay.
Well, the only thing that happens is the forward one. But to define entropy, we compare this guy with the backwards with the reference. If you can distinguish these guys, then entropy appears.
Okay, so it's due to the lack of information in the fluctuations.
It's not actually. Think about the chaotic dynamics. So a chaotic dynamics is a closed system. You have a closed phase space, and chaotic dynamics has a trajectory there because deterministic K is deterministic. But the problem is that as time goes on, you have structures being developed in smaller and smaller scales of the phase space. This means that it's getting harder and harder for you to follow the dynamics. The rate at which these structures are formed is exactly given by the Lyapunov exponent. Actually, Kolmogorov-Sinai entropy is the sum of the positive Lyapunov exponents. So that's the rate that you lose information. And this generates, so the information is there, but you cannot access because it's split in so many degrees of freedom that you cannot follow.
Okay.
That's the main thing. That's the way I see these things.
No, nice. That's a nice view. Right. Thank you.
So it's just related to this question. So is it because of this formula there? Because like
no, this formula just quantifies these.
No, yes, but I think the question was how can we see irreversibility of a process by the theorem? And this formula basically says that if sigma is 0, this probability is matched, right? I can
yes, exactly. So the process is reversible.
Right, but for any sigma positive, you say that that the probabilities have an imbalance between each other, and this is what you define to be an irreversible process.
Exactly, because it's exponentially more likely for you to observe the one in the forward than the backwards.
In the backwards. Okay.
So just one quick question. So for the Crookes theorem, you assume phase space, right?
But in the classical case, yes.
Yes. In the quantum case?
No, the quantum case we don't have. We restart this now. We don't have phase space. Well, we have phase space, but we have many phases, different phase space. But we will not assume phase space because there are no trajectories. Yeah, these guys were already based on the level of trajectories in phase space. In quantum case, we cannot do this.
Okay.
Yeah, but this will be up here now.
Okay, fine.
We still have time, no? Okay.
In some slide, you said that Markovianity would play a role.
No, I just said that I'm assuming Markovian.
Yes.
Yeah.
But where is this entry in the derivation? This was not clear to me at which point you assume Markovianity.
Yeah, I'm just assuming that the dynamics follows a Liouville theorem, which means that it's given by Hamiltonian flux, so it must be a Markovian dynamics. I'm just assuming because non-Markovianity here. I mean, what do you mean? If I have a system interact with an environment, fluctuating environment, and these interactions leads to non-Markovian dynamics, then information can come back to the system, and then you can have decrease of entropy. But this is a different thing. but we are assuming no Markovianity here. In the quantum case, the Markovianity will be in the unitary evolution. So it's always no Markovian. So more questions? No, let us go to the quantum case. The quantum case, we do the same thing. We have a Hamiltonian. That depends on some external parameters or a set of parameters, actually. And the process takes place in a finite time interval. And the system is initially in thermal equilibrium. We develop lambda in the initial time. So that is defined by the Hamiltonian here. The evolution is unitary, because it follows Schrödinger's equation. And then it came the question, what's the work done on the system or by the system? It doesn't matter. It's just a change of sign. But in classical mechanics, it's easy to do this because you just integrate the power over the trajectory and that's it. But here we don't have the notion of power actually, and don't have the notion of a trajectory. So we cannot simply do the same thing. And we have several definitions of work. Most of them are not compatible, not fully compatible. And this is still under debate. I'm going to use the most used one in literature. So how do we define this thing? It's called a two-point measurement scheme. So we have to make two measurements. And then enters half hour question in the beginning. The measurement is just to define the energy. But the dynamics between the measurements is unitary. So that is what matters for being reversible, is the between measurements dynamics. So the initial probability at time t equals 0, we simply measure the energy. We make a projective measurement in the 8-knot eigenbasis. And we get this eigenvalue here, is the eigenvalue of the Hamiltonian with this probability. That's the usual Born's rule of quantum mechanics. And then we let the system evolve. This guy here is the time ordinary operator, so just usual, the solution of Schrödinger's equation here. And then at another time, we measure the energy again, but we measure in the, there is a typo here, this is supposed to be tau, the Greek letter, not. We measure the energy and we get the eigenvalue, this eigenvalue with this conditional probability. So if we made the first measurement, then the state of the system just after the measurement is just an energy eigenstate of the system with the projector here. And then we evolve the state of the system unitarily, and then we make another measurement. It is the projector in the final Hamiltonian eigenbasis. So we get the conditional probability of getting the eigenvalue m, given that we got n in the first measurement. So that's the usual Born's rule. And then it comes the problem. Which here, we define work like this. Then we say, look, here we were in thermal equilibrium. We can simply say, look, the energy of the system is this guy, but I don't know exactly, the energy of the system is defined, but I don't know exactly which one is this. So I measure, and the system is in a given eigenstate, because we have a thermal distribution. But then the system is a pure state, and it evolves under a unitary evolution, which takes to a pure state. And this pure state can be a general superposition in the final Hamiltonian eigenbasis. In general, it is. And then you say that you make the second measurement, and the energy of the system is this, the result of the measurement. But this is not the energy of the system. I mean, the energy of the system before the measurement is not defined, because it can be in a huge superposition. So we cannot say that the value of this guy is defined. But that's the way we define work. And apparently this works in several situations, not all of them. First of all, you kill coherences here. When I make the second measurements, you kill all the coherences in the energy eigenbasis. So you need to take this into account. There are ways to take this into account. what's the actual dynamics of the system, what's the actual contribution coming from the quantum dynamics of the system to these fluctuation relations. There are modifications of these guys, but in general, we are not interested in these things. Of course, if anyone is interested in these things, just knock on my door, and I show all the references regarding the study of quantum coherences and other effects, other quantum effects in these things. But that's the thing that we need to accept here. The definition of what we call quantum work, okay, is defined just like this. Once you have these, we just define it in the same way we did the forward protocol and the backward protocols. Did I answer a question about how the thing? Okay. We don't need trajectories here. So the forward is just the usual one, and that's the transition probability. So that's the initial probability times the transition probability. So the definition of joint probability, conditional probability actually. The backwards we define like this. This is the anti-unitary operator, time reverse operator. So it doesn't mean that this is equal to U dagger, but we need to apply this guy to the evolution. Then we have the time reverse operator, and then we prepare the system in the equilibrium, but defined by the final Hamiltonian. And then we do the same thing in classical physics. We just measure the guy in the final Hamiltonian eigenbasis, and then evolve the guy. This is the initial state. We measure the guy. We evolve the guy for backwards in time, and then we measure the initial energy. And then we have the distribution probability to the reverse process.
What is this theta function there?
Theta is the time reverse operator. It just reverse the evolution. We can pick up in a simple situations, we can say that we change U by U dagger, but this is not always true. For instance, if you have magnetic fields, then this is not true. We have also to invert the direction of the magnetic fields. And in general, this is it's an anti-unitary operator that reverses the flow of time. Not the flow, the direction of time.
This theta has some sort of universal
properties.
Can you write down this theta, or it depends on the
specific
no.
System? We write down the properties of this guy, the action of these guys in some in the systems, in quantum systems. But this is well defined. I think that every quantum mechanics textbook we have this in the appendix. But it's not unitary; it's anti-unitary because they reverse the time. But the properties of this guy are very well understood. How they change the Hamiltonians, how they change the systems is well defined. So it's called a time reverse operator. No. It's a different thing. That's why I put the big theta here, but the small theta for the Heaviside fund. They are different things. It's just, this guy just reversed the time of the dynamics. It changed the sign of time.
For that definition to be non-trivial, some sorts, like the time evolution, the generator of the time evolution must have a different spectra than the E0 and EMN. In some sense that there is some.
Sorry, I didn't get.
Like what I mean is that because you have some reference Hamiltonian that you are measuring the energies, right?
Yeah. Oh, no, not reference Hamiltonian.
Oh no. Yes, the H0. Yes.
Yeah, that's the Hamiltonian that starts at H0 and then goes to a tau.
Yeah. Okay. So in this definition, we must have that like in the time evolution, the Hamiltonian in the middle, say in the sometime intermediate time, must have a different spectra than the ones that we begin and end, right? Like it should be some sort of.
No, it doesn't. It doesn't need to be different. It can be two harmonic oscillators. Okay. It doesn't matter. The important thing here, if I have a harmonic oscillator that I just change the the size of the gap. But I change everything. So it's exactly the same system before and after.
I see.
Yeah.
Okay. I see.
They have the same spectrum. But the problem, the thing is that this guy should be not zero. So the transition probability should be not zero. So entropy will be related to transitions in the energy eigenbase. If this guy is zero, then nothing happens. The important thing is this guy. But this guy generates coherence. When I have transitions, you have coherence being generated in the energy eigenbases. So let us think about whoa, that's too much. Let us think about Star-Gerlach experiment. Star-Gerlach experiment, we have the forward process, the emission of the atom here, and you pass over the filter and goes through the magnet, and then you reach some point in the screen. How do I revert this thing? I must come here, I get up from here and go back. But then I revert the momentum, the linear momentum of the guy, and revert the direction of time, but then I have to change the direction of the magnetic field. Otherwise it goes other way. And that's what the theta does. The theta does this operation. It reverses the entire dynamics in time. So we have everything that we need, both of them, and then we do exactly the same thing. We just compare this guy with this guy. That's what we want to do. And then we can write this thing like this. Is not difficult to do. And then we simply from this we can define the work probability density distribution, which is just given by this is the Dirac delta function. Exactly. Oh, here's the minus sign. For the forward and backward, then we simply divide these guys like here, and then we use the properties of quantum probabilities here and use the properties of Dirac delta function. It's easy to show that this is the result, which is exactly the same thing. It's exactly the same equation as that one. So the form of and by multiplying this guy by this guy and integrating and taking into account the conservation of probability, you get direct. The quantum Jarzynski equality, which is exactly the same thing. The only thing that changed here is the definition of work, because this guy is the same thing because we were talking about equilibrium distributions. So the difference in free energy is just the difference in free energy. Now it's this partition function of the guy. You define all of these things. And then you have exactly the same theorems, and that's and then this fact makes people think about what are the quantum dynamics here, what are the quantum effects here in this thing, how quantum dynamics enters here, and then we have plenty of studies relating quantum coherences and other things. But the problem is that you make measurements. And when you make measurements, you kill coherences, and we still don't know exactly how to define this thing. We have many definitions. We have a plenty of them actually. Most of them are incompatible with each other. This guy that I used has some interesting properties, but we don't take actually quantum effects into account. So we need to take quantum effects into account. So we need to avoid measurements, which is very hard because then how do you define work? Energy is always defined, average energy at least. But the problem is how to split work and heat. That's how to split energy into work and heat. That's the difficult thing. In classical physics, it's unique, but in quantum mechanics, we don't have these things because exactly we don't have quantum trajectories, so we cannot. And these guys, work and heat, are trajectory dependent. That's one of the things that makes difficult to define these quantities also in general relativity. Because that's why actually we cannot compare. That's one of the problem that we reach because we cannot compare energy of the system in different points in space-time, because the energy depends on the trajectory that I choose to come here, but I can choose infinitely many. So there is no way to compare energy. So how to define these things in the relativistic context, we will see on Friday. But before we needed to fully understand these things and what general relativity is, actually. And okay, it's a little bit more 1 hour. For today's, that's it, folks. Well, I'm fully open for questions, and also, my office is 102 on the second floor here.
I have a question. Probably I'm not very familiar with quantum stochastic theory, so
Quantum?
probably this quantum stochastic theory. So I probably this is a naive question or a very simple question, but how is the difference from stochastic process for a quantum stochastic process? What's the main difference? I mean, you make some kind of stochastic quantization or something like that?
No. Here we actually don't deal with these sort of things. I mean, the process here is unitary, just unitary, and this is I don't know if I fully understand your question, but this is just the definition of probability in quantum mechanics. Yeah. This is Born's rule. I mean, the usual quantum mechanics. I'm just doing usual quantum mechanics here. So that's the way we define probability. That if I measure the system that is in a thermal state, the probability is going to be this. And that's the evolution of the initial state and the measurement. Again, so this gives me the conditional probability, according to Born's rule of quantum mechanics. I'm not studying stochastic process or anything like this here. I'm just using basic quantum mechanics. But there are differences in stochastic process in quantum mechanics and classical mechanics, and they are huge. Yeah.
Thank you.
Yeah.
So, just one question because. So, are there different dissipation, fluctuation dissipation theorems, or are all of them the same?
Well, remember that I started with Einstein relation and then Johnson and Niki's relation that is the same thing but for resistors, for electric circuits, and then I showed the general green cube theorem. That embraces all of these theorems, but for linear response.
Okay.
This goes beyond linear response. This is the general one.
I see. Okay.
So you can write this thing in several different ways,
so,
but it's the same thing.
So, for example, the fact that this one coincides with the classical case, this is like a property of all the dissipation theorems.
Well, under these definitions.
Okay.
If I change the definition of work, for instance, then things will be different.
Okay. Okay.
That's that. Actually, I can define if I do this thing, but forget that I'm measuring energy. I measure some other observable. It doesn't matter. If I measure here some observable and then here another observable, a different one, putting, of course, take into account dimensions here, but I can simply define the difference between these two outcomes, and it's going to follow exactly the same thing. But in the end, it's not going to be the difference in free energy.
I see. Okay.
That appears there, because difference in free energy comes from the assumption that the initial state is equilibrium one. But actually, any two measurements that you make and you define this stochastic quantity here, it is going to end in this exactly the same thing here, but this thing is going to be different.
Okay.
It's going to be a number, independent of the process, independent of the average, not stochastic quantities. There's a number that's not going to be interpreted as difference in free energy, but it's related with the measurement that you made. So the thing is that once I define these things and the setup of the process, then it follows from basic rules of quantum mechanics.
Okay. Okay.
Okay. So there are any other ways to like prove the same statement but using different kinds of work definitions? I don't know.
Well, there are some other works that work on this, but the result is different. I mean, I usually don't work with these things. I just consider this definition up to date because this is the most used one. But there are people studying different definitions of work. On Friday, I will talk about a different one that I proposed myself in the colloquium, not here. Here, I will assume that this is the case always. But things will be different because you define things differently. Note that the most important thing here is this guy, that you are calling this guy the energy of the system, and it's not. I mean, we after the measurement, yeah, you can say that the state is that one. We define the energy, but before the measurement, there is no way to do this. But I mean, I would say that that's the best thing we can do today.
Yeah, so you cannot say like a process is irreversible if you not measure it like in that definition, of course.
That's the problem in quantum mechanics, and we need to make measurements, and then one of the problems is how to take the measurements into account. I mean, how to put the measurements into the process, because we can do this in the following way. We just turn to information theory and we describe the measurement as a quantum classical channel, and then we put the capacity of this channel into the calculations. But then you have to remove the reversibility associated with these measurements. And if you are interested just in the reversibility of the process itself, but the measurements will for sure introduce these things, but it can be taken into account. There are people that study the thermodynamics of measurements.
Thank you.
So the Crookes theorem is beyond green Kubo theorem.
Yeah, it's linear response. Yeah, it's beyond linear response.
Because you include all types of perturbations, interactions, and this kind of thing. So my question is, can you derive a relation between the probabilities of the forward and reverse process using linear response theory, something like that? Not the exponential, not this relation, but a similar relation?
Well, you can. I don't remember to solve this thing because usually it's stated into the as in terms of the response function, the correlation functions. Even for quantum field theories, they do these. But I think that's possible to do this. I never saw this calculation, but I think that is possible to define the probabilities, but under the restriction of linear response. Because we can simply remember when deriving the Kubus theorem, we use the Schrödinger's dynamics. So if you have Schrödinger's dynamics, we can simply compute probabilities from that thing. Instead of computing the response of some function, we just compute probabilities. We can do the same thing, but restrict to linear response. I mean, just instead of put the entire U here, you just put you just put the first exponential of this guy, the first term in the Freeman series, a Dyson series here.
But we can expect that the result will be this exponential behavior.
No. It's not going to be. It's going to be some function here, linear function. It's going to be different from this guy because this is the full response. So I expect a different thing, just linear when this guy is not big. You have just a small amount of entropy being produced. So, but the way I think is this is just replacing this guy by the first term in the Dyson series of this guy here, and then we have linear theory.
Thank you.
Oh, thank you.